I challenged a software engineer with zero board design experience to create his very first PCB from scratch. The rules. The board must include a microcontroller. So it's not like super simple board with one resistor or something. The second rule, he had to work all by himself, using only online resources like YouTube tutorials, no direct help allowed. The third rule, he had just 4 days to plan, learn, and design the board. After 4 days, he shared his project with me and I sent the board to production. So, how did it go? Did the board work or fail or go up in flames? You will see. That's what this is all about. So let's start by checking out the schematic. This is the schematic, and the very first thing what I noticed, there is no project name. So very often at the top of your schematic page, you would like to place the name of your project, because when someone opens your schematic, they would like to know what is the schematic about. Okay, and also maybe down here, most of these, it looks like default values. Maybe you would like to put here your name, again, maybe project name, and also here, you don't want to use the default names, board 1, schematic 1, put there maybe like my first board or something like that. But otherwise, I would like to say I really like that here we can see the description of each block. We can very nicely see what each block is doing. So putting these descriptions into schematic, that's a very professional way how to draw your schematic. Always do this, then it's very easy to read the schematic. The organization of these blocks, it's okay. So if I would be drawing this schematic, maybe I would place these Arduino headers on the right side of this schematic page. So this is good. Maybe I would place this microcontroller a little bit into middle, and maybe I would place this USB connector a little bit up and connect it directly to the microcontroller. So it's very clear how this USB connector and microcontroller are connected together. But otherwise it's okay. It's perfectly fine. What I would do, I would probably update this symbol a little bit. So very often you will find in the symbols, you will find these power pins at the top of the symbol, so this is good. And you will find the ground pins at the bottom of the symbol, so this is also good. But I would probably place these USB pins here on the left side of the symbol, and I would connect the USB connector there. And I would maybe place these crystal pins, these which are here, I would place them maybe somewhere down here, so we can place the crystal here. And I would leave these boot and reset pins here on the left side. Very often, when you see this kind of symbols, the control pins are on the left side, and the kind of output pins, they are on the right side of the symbol. So maybe that's how I would organize this. Next, what we may need is datasheet. So I'm going to open datasheet. And also, maybe I would like to find some kind of development board or something. I'm going to click here. So this is the chip. And maybe here in tools, let's have a look. Oh, here are some boards, so maybe we can, this one looks like Arduino board, so I'm going to click here. Cut resources. And I'm going to open the board schematic. So basically, if we don't know how to connect something, we can go to this reference schematic and double check how they connected in here. We know this board is working, they sell the board, so this should be connected correctly. And also, when designing our board, maybe we would like to make it compatible with this reference board. It means then we can, for example, use some kind of software or code which is written for this reference board. We can use it also on our board. The first thing what we would like to check in our schematic is how these power pins are connected. So we have 1, 2, 3, 4, 5 power pins, and usually when you are connecting a chip in your schematic, you would like to have one decoupling capacitor per pin, and the standard decoupling capacitor value is 100 nanofarad. So we would like to have 5 100 nanofarad capacitors here, so we can then place them in our PCB close to each of these pins. So we need 1, 2, 3, 4, 5 100 nanofarad capacitors. That's good. And then there is one bigger 10 microfarad capacitor, which we can place somewhere close to this microcontroller. Okay, so this is perfect. What I would like to double check is the voltage. So first I'm going to double check what is the voltage of these capacitors. 16 volts. That's perfect. I would like to double check if they are all the same type. So look here, and they should be all the same type of the capacitors. And this is good because you would like to keep different types of the components on your board on the minimum, okay? Because there are many 100 nanofarad capacitors. You would like to use the same 100 nanofarad capacitor, so it's easier, it's cheaper to build your board. Okay, let's double check also this one. Also, this one is a little bit bigger, 0805. These are smaller. These are 0402. And this one is 25 volt, so that's okay. We can close this. This is good. Now, this is the analog power or reference voltage, and you can see it's connected a little bit differently. It's not connected directly to 3.3 volts, but there is ferrite bit and there are some capacitors. So we are creating a filter here, and I guess this is based on the reference schematic. So it is connected to pin number 13. Here I can see it's down here. Pin number 13. This is the analog voltage. There is 100 nanofarad capacitor and there is a ferrite bit. So we have it a little bit differently, but it's okay. 10 nanofarad, 1 microfarad, 1 microfarad. This is okay. What could be interesting is how to select this ferrite bit, and also the question is if we really would like to use ferrite bit. I created a video where we discuss if we need ferrite bits in power rails or not. In this case, it should be fine because this is low current pin. Also, we know it's working fine because it is used in the reference schematic. What you may need to be careful about is you need to be sure to double check at least the current, maximum current which can flow through this. This is very low current, so it should not be a problem, but we can have a look. Okay, didn't recognize the component, so I'm going to find it. And we are looking for the maximum current. 800 milliamps. Okay, so this is fine. We don't need to worry. Perfect. So if I would be doing this, maybe I would put here 0 ohm resistor, I don't know. And if there would be problems, then I would maybe play with ferrite bits. But there is one more power pin, this V cap. This is important pin. So again, we can check it in the reference schematic. Pin number 30, how they connect it. Pin number 30. It is here. Pin number 30, 4.7 microfarad capacitor. You can also, I guess, search for V cap in datasheet. It should tell how to connect it. I see. Table 16. 4.7 microfarad. So it's good. You can also always double check this information in datasheet. What I would do, I would probably name this net because it's kind of important net. This capacitor, maybe we would like to place it close to this pin and connect with as short track as possible. So I would probably name this. We started talking about power, so let's have a look how the power is connected. Here is the voltage regulator. This is the 3.3 volt, main 3.3 volt for the microcontroller. We are making 3.3 volts from these 5 volts, and there is one more regulator here, which can make 5 volts from external voltage input. These regulators, they are kind of same, just the output is a little bit different. So what we can do, we can open datasheet and we can have a look how they recommend to connect this. So here is the typical application, 22 microfarad on the output and 22 microfarad on the input. And that's what we can see here, okay, 22 microfarad, and also down here. So this looks okay, but we need to be careful. These kind of regulators, they sometimes are very specific about what kind of output capacitor we should connect here. So it's not only about the value, but also about specific type of capacitor. And what we can do, we can find more information here. Very often there is a section. Stability. This is what we are looking for. Stability. Addition of 22 microfarad solid tantalum capacitor. Okay, we have a look. So what is this? 25 volt, 22 microfarad ceramic capacitor. It's not exactly what they are recommending, but from my experience, usually it will work. But I wanted to point this out because sometimes there may be some occasions if you connect this kind of regulator wrong way, if you use wrong capacitor, it may not work properly. So be careful, okay, when you are connecting something like this. We can keep this 20 microfarad capacitor, ceramic capacitor. We will see if it works okay. When I'm looking at this symbol, there is something unusual. So first, again, I would maybe update the symbol. I would like to have the output on the right side, inputs on the left, ground on the bottom of the symbol. But what is very interesting, the output is on these 2 pins. So if we go up here, I would like to see how the pins are connected. We will be using this kind of footprint. You can see 1, 2, 3. They didn't put here. There should be number 4 actually, because it's very hard to say from this picture where this is connected. I guess it's tab is output, so this is tab, so it's going to be output, but it should be in datasheet. And you can see 1, 2, 3. So 2 is V out. So also the tab will be V out. And I try not to use this kind of pinout because these kind of chips, they can get warm, they can get hot. So what you need to do on your PCB, you need to somehow find a way how to cool down this chip. And one of the ways how you can cool it down is you can make a big copper area around this pin, which is here. And if this pin is V out, then you need to create the big V out area, which is not always possible. It's much better if this pin is connected to ground, because very often if you have multi-layer PCB, you can put there vias, and ground is very often almost everywhere. So if this is connected to ground, you can spread the heat from this chip much better than if this is connected to output voltage. So I wouldn't use this kind of footprint with this kind of pinout if it's possible. It's just a small tip what I learned. Also this connection, which is here, it's not something what I would do. You know, in schematic, usually you have two kind of crossing, or wire crossing. So this is one kind of wire crossing. So here is a wire, and here is a wire, and they are crossing here. And this is second type of crossing. Here is a wire, here is wire, they are crossing. So here they are connected, here they are not connected. And I've seen number of schematics where the mistake was made because something went wrong with this junction which is here. The junction could disappear, or by mistake it could be placed there, and then by mistake this would be shorted, or by mistake if the junction is not here, this would be not connected. It can happen when you, for example, copy and paste this circuit which is here. Maybe it can disappear by mistake. You may not copy it correctly, or it may not be redrawn correctly. I've seen it. So I don't like to draw this kind of connection. This is fine. So if I see cross like this in my schematics, I know most of the time there will be no connection between them. I try to avoid drawing this. I'm sure you understand what I mean. Now it's not so big problem. In today's CAD softwares, it's not big problem. Usually when you do copy and paste, it will copy it correctly. But even if you like print your schematic, or sometimes this may not be very well visible, so you may think it's connected and it's not connected. So just don't do it this way. We would like to double check also the these capacitors. What is the size? 12 of 6. It's quite large. Maybe, I mean, size is quite large of this capacitor. Maybe there may be smaller capacitors. So I like to use smaller capacitors. In this case, it's not really important because the board is quite large, and very often these bigger capacitors are a little bit cheaper. But be aware what kind of size of components you would like to use in your board. I have few more notes about this regulator. So first, I would place some kind of information what is the maximum input voltage which we can connect to this chip, and what is the maximum current of this chip. So just put like text box somewhere here and put this kind of information here. So you know, you don't have to, or anyone, if the information is not there, then people have to open data sheet of these and they have to double check what is the maximum input voltage. Just place it directly into schematic. Also, you need to be very careful. As I said, this chip may get very hot if the voltage is too high, and if the current driven by this circuit what we have here, or probably or possibly something what is connected to our board, if it's driving too much current, then this can get like very, very hot. Be very careful about linear regulators. To select the power for our board, we will use this power selection header. So in this header, we will use a jumper, which will connect between pin number 2 and 3 to power up the board from the external power supply, or we will place jumper between pin 2 and 1 to power up the board from the USB. It's very clear that we will need a jumper. So I like, here is a note, use jumper, but in my schematic, in this situation, I would actually create a specific symbol for jumper, and I would place it here. So it would be symbol with no pins, but this symbol would be included in BOM, bill of material. because this jumper is very important and we don't want to forget to buy it when we will be building this board. Without this jumper, this board is not going to work. Also, very small detail, in this kind of situation, when header is used as a jumper, I may rotate it by 90 degrees. And also notice these powers. So once I use power symbol like this in my schematic, then I will always use it. So here I would not use these net names, I would use this power symbol. Okay, so these are net names, this is power symbol. And in some cases I may use net name for power, but only for very local power. Because be very careful, these net names, in some cases, they may not go through multiple pages. So if you have this net name on one page, and if you have same net name on different page in the same schematic, sometimes they may not be connected. It depends on settings, project settings, it depends on the software what we are using. Sometimes they may not be connected. Be very careful about this. These power symbols, they are global. So if you use these power symbols, by default, they are always connected on all the pages in your schematic. Also, what I noticed, and it's very good, on all the powers, he used the plus sign. So plus sign, it means it's a power, and also he used the voltage. So this is very, very good. I like this approach. I always do it exactly the same way, because then it's very clear. This is power and this is the voltage what I should measure when I use DVM. We also have this power LED placed directly on 3.3 volts. Again, very good, because you could place this power LED also on 5 volts. But if you place it on 3.3 volts, it means when this LED is on, then you know the 5 volts and also 3.3 volts is correct. If you place this power LED only on 5 volts, then if 3.3 volts is not working, the LED will be still green, and you may think like, oh, everything is working fine, and 3.3 volts may not work. Okay, so always place the power LED on the last power, which is switching on as the last one, so you know all the other powers are working properly. And when we are talking about these LEDs, so he used 1 kilo ohm resistor, and he connected the LED symbol correctly. Be very careful, you need to connect it correctly. Very often I use 1 kilo ohm resistor as the initial value for standard LEDs, and then when I build the board I may adjust the value of this resistor based on how bright this LED is, because there are big differences between LEDs. Some of them they may be very bright, some of them they are not very bright, so I will play with the resistor value later. You need to place there the resistor, okay, because you need to limit the maximum current flowing through this LED. Usually it's a couple of milliamps, so you need to put there this resistor. Initial value 1 kilo ohm is perfectly fine. Next, what we would need to make this work is this boot and reset. So first we can have a closer look on this boot. I think in reference design where is it connected? Pin number 60. In the reference design they connected it a little bit differently. Boot 60. They only have pull down resistor here, and then it goes somewhere. Here, this is very easy way how to control the level on this boot pin. Boot pin, we use it if we would like to flash firmware of our microcontroller through USB. So basically we can use this very simple switch, which will by default we use it to connect it to ground. It means it will boot up normally, and if we would like to update the firmware, we will just put this boot switch into this second position, and then we refresh the microcontroller. All this information should be placed here, okay? So here again, place text box and explain when boot 0 is high, then when boot 0 is low, then this is what is happening. It is very helpful because then people don't have to go to datasheet and search for the information, and they will directly from the schematic they will understand what is this boot signal about. Reset. This is not how I would connect the reset pin, but again, I think this is exactly what is used here. Yeah, here is the reset. They used the power or the reset button and the 100 nanofarad capacitor in parallel with the reset button. What I really don't like about this, I don't like to do short circuit on capacitors. So if you press this button, you will directly short circuit the pins of this capacitor. You should put there maybe some kind of resistor at least or something to limit the maximum current. And also there is no other external component. Very often for this reset circuit you would like to put there maybe as I already mentioned, some resistors or maybe even some diodes. I know there is some circuit inside of this microcontroller, so there is pull-up inside of the microcontroller. I guess there is also like ESD protection diode inside of the controller. So when you disconnect the power, then this capacitor should be discharged immediately. But again, it's going to be connected kind of directly through the ESD diode or something. As I said, I don't like this kind of connection. They have it in their reference design, so maybe it's just perfectly fine. But it's not something what I like to connect this way. But I need to say, I'm very happy that this is connected correctly. I've done so. I created mistakes in this kind of connections. Watch how this switch or this button is connected internally. So you can see this pin 1 and 2 are connected together inside of the switch. And these pins 4 and 3 are connected together inside of the switch. So be sure you connect these pins correctly in this circuit, because you can very easily make mistake if you rotate this switch. I've seen many mistakes done this way. I've done this kind of mistake in past, and yeah, it's not it's not a very nice mistake. You have to then cut the PCB to make it work. Next very important thing what we are connecting to this microcontroller is this crystal. So we don't really need this crystal because there is internal oscillator, but we would like to run it maybe at maximum frequency. I guess that's why he used the 26 megahertz crystal. I think this is the highest frequency what can be connected to this microcontroller. But we need to be very careful. This kind of circuit is very sensitive to capacitance. So you need to be sure you have the correct capacitance of this crystal, and you have correct capacitance connected here. There are equations how you can calculate it. If you are not sure, you can double check the original reference schematic. So if we have a look here, you can see here they recommend 20 picofarad, 20 picofarad, and 8 megahertz, 16 picofarad. Okay, so we have 26 megahertz, but that's not really important in this case. We have to double check the capacitance of this crystal, and it's 12 picofarad. So it's not 16, it's 12 picofarad. So maybe you would need to double check what kind of capacitors you need to fit here, because this 20 picofarad is probably calculated for the 16 picofarad crystal. If you would like to know how to calculate it, I think it will be probably somewhere in datasheet. Let's find more information. Here, high-speed external clock generated from crystal ceramic oscillator, 4 to 26 megahertz. For information on selecting the crystal, refer to application note, this one. So we need to search for this. I'm going to open it. And here, go through this document. There will be some equations and they will exactly tell you how you should calculate the capacitor values. Okay, but I'm not going to talk about this because I only would like to, oh, I didn't want to close this. I only wanted to point out, be careful about this, okay? Because this is very important circuit. If it's not designed correctly, it may not oscillate and then your microcontroller will not work with this external crystal. Oh, also what I would like to say, I noticed he named these nets for this crystal. That's very good because these are very important nets. When you will be doing PCB lab, you would like to know you are routing the crystal tracks. So this is very good. Always name very important nets. Now we can talk about this USB connector. So this is a good connector. There are different kind of USB-C connectors. We don't need USB 3, so we can use this one with the reduced number of pins. And also when you are selecting USB-C connector, maybe you would like to use the one with the with only one row of pins. You don't want to have pins in 2 rows because second row is very often under the connector. It's very hard to solder it down. So this is a good connector. And for USB-C, to deliver 5 volts, you need to use these pull-down resistors on these CC pins, so this is correct. And what also you may want to connect, there is ESD protection. So this looks okay. We can double check how he come up with this ESD protection and if it's correct one. So I'm going to open datasheet and it says here applications USB 2, so that's good. And also we can have a look how they connect it. Is here some information? Here. So here is V bus, so this is 5 volts. Then there is ground and there is T plus T minus. Here is also a capacitor. Oh, here is also something. 100 nanofarad. So there should be 100 nanofarad capacitor close to the VC, the pin which is connected to power. So here should be 100 nanofarad capacitor. And also I noticed in whole schematic, I noticed always when there is power going out or going in to your board, I would recommend to place there at least 100 nanofarad capacitor. It may help with filtering these power rails. So I would add 100 nanofarad capacitor also here, close to this one here. Otherwise it looks it's connected correctly. So this is minus and this is the negative, so that's okay. Plus, positive, okay, they are connected, okay. Be very careful, you can make mistakes in this. And also these nets, they are not named. You can see name, there is no name here. This is USB, here is no name. These nets are very important. You really would like to place names here. Okay. Next, we can double check the connection here. So I'm going to close this and I'm going to open this reference design. So I think he connected these Arduino connectors or headers exactly same way as they have them in the reference design. So we don't really need to be worried about like connection here because it's exactly same. It means software will be compatible, so that's very good. And next we can also have a look on this user LED, because I think here they connected it a little bit differently. Maybe this green LED it's the user LED and it's connected to PA5, and he connected this to user LED PC12. I don't know why. I don't really know why, but it means that this LED it may not be software compatible with the default software for this reference board. What is also very interesting, very often when I connect LED to GPIO pins, actually I control this side of the LED. I connect this to power and I control this side. I will connect here the pin of the microcontroller. There are a couple of reasons. One reason is, for example, if it's possible, I don't want to drive the power through the pin of the microcontroller, because in this case we can drive it directly from the power rail, so why not? And also sometimes these LEDs, they may be connected to chips with open drain outputs. So if I control this side of the LED, I always know it's going to work, even if it's open drain output. So these are like kind of two biggest arguments why I normally connect these to plus and then control this side. Normally I don't control LEDs this way, but if you connect it the other way, comparing to this reference design, then it's going to be reversed. Yeah, so in the reference design, when it is on, then on my board it would be off, and the other way around, because here I'm controlling the LED will be on when the pin is low, but in this case what they have here, the LED is on when the pin is high. Only what left are these two headers or two connectors which are here. This is not something what I would do. I'm super careful about connecting headers, how the pins are ordered on headers, and this connection, what we can see here, what may very easily happen, by mistake you can connect the header the other way around, and then basically you will be connecting 3.3 volts to ground and ground to 3.3 volts. So anything what you will be connecting to this header, there is possibility that you may damage that device if you connect it the wrong way. When you are designing pinout for headers, you would like to maybe think about what's going to happen when someone by mistake connect the header the other way around. So maybe you could add one more extra pin and organize the pins a little bit differently, so even if they connect it wrong way, nothing will happen. Sometimes, for example, in this case, what will probably happen, the board what you are connecting may be damaged. So your board will be safe, but the other board may be damaged. But there may be situations when maybe your board could be damaged if it's connected wrong way, and you really don't want to have this situation. If you are going to sell thousands and thousands of your boards, there will be people who will connect this header wrong way, and you really don't want then people damage your board and sending your board back. Okay, be very careful about this kind of connection. This is connected directly to SDIO and clock. We don't really need to check this. I think this is like a very simple connection, and this UART. When I was checking this UART, I don't know exactly how he would like to use this connector, but there is special feature on this UART. I'm going to find it. Here. So there is a special feature on this UART1. When it's connected to PA9 and PA10, then it can be used to reprogram the flash memory. But in this board, this UART1 is connected to pins PA15 and PB7. I don't know if this feature is going to work if it's connected to these different pins, alternate pins. So I would, if I would add this header. I would maybe connect it to these pins which are here, PA9 and PA10. Okay, and I think that's kind of everything about the schematic. Let's have a look on the PCB. And before we go and talk about this layout, I would like to see 3D model. So I'm going to open it. And that's the end for part 1. The link to part 2, the layout review, is in the description. If you would like to learn more about how to design boards, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye!